We've been building a simulation world that so far is pretty straightforward, but it doesn't take much for the problems that we face to start to get tricky. If we simply want our creature to figure out what is the best place to go to find food and how do we get there when there are obstacles in the way, that's a path searching problem, and it turns out that's not easy to do. That's an example of what the field of computer science has come to call artificial intelligence. Artificial intelligence is a nebulous word. It means lots of things, and it is not really well defined. But you will find people using the term artificial intelligence when they're talking about natural language translation, right? Translating something from English to Spanish or Chinese. Voice recognition, right? Having the computer on your phone recognize what it is that you're saying. Image recognition, taking a picture of something and having the computer know what is the contents in the picture. Having a computer system adapt to the information it's presented with to improve its ability to do the above things over time. And game playing. Suppose you want to play a game against a computer. If you want to play chess and the computer's playing back against you, then well, that's artificial intelligence, right? That's doing something that we traditionally have thought as being only things that humans can do that require intelligence. Computer does it, it's artificial intelligence. But on the other hand, all of the solutions to those problems are just algorithms, right? They're computer programs. They're not intelligent. They are just software executing in exactly the same way we've been writing software so far. So is it artificial intelligence, or is it just software? Well, it's kind of this philosophical question, and because of that, we often think of artificial intelligence as being software to do things that humans do that computers cannot yet do. But once computers can do them, sometimes we don't think of them as artificial intelligence anymore, we just think about them as programs. And so there's a funny way of thinking about it, which is that whatever AI is, if a computer can do it, it isn't AI. AI has a long history. One of the people that is best known for helping to create it is a professor named Marvin Minsky, who's been at MIT for a very long time. He's written lots of papers and lots of books. One sort of broad access book written, I think, in the 80s was The Society of Mind, which I read when I was in high school, and it had a big influence on my professional development. I was quite happy when I got to see him when he came to visit University of Maryland a few years ago. But of course, it's a huge field now, and there are lots of people all over working in AI, including several really excellent people at University of Maryland. Let's take a quick look at what some of the kinds of problems that AI typically tries to deal with are. An important one is classification. Classification is simply, if you have a bunch of data items with different characteristics, can you tell what kind each data item is? So let's look at this simple example. We are listening to some recordings of instruments, and we want to be able to figure out what kind of music is being played. Is it opera, or is it jazz, or is it pop? Well, a human can tell pretty quickly, but can a computer do it? Well, how would a computer do it? Well, here's a very simplistic way, which is you can look at some metrics, the mean vibrato rate and coverage. If you take some metric, some way to measure your data and plot them, you will see that if you have ground truth, that is, if you have had a human label your inputs, you can start to see some patterns. And so look, the opera are pretty well separate in this two-dimensional space from these other items. Except, notice, this red triangle shows that this one opera, in fact, looks a lot like flamenco. And so, if you were to try and distinguish between opera and flamenco using only these two pieces of data, you wouldn't do a good job. And in fact, even if this was good enough, how would you write a program to automatically figure out that these ones go together and these ones go together, right? This picture shows them being drawn with different colors and shapes, but when the computer sees them, they're all just points in a data space. So coming up with an algorithm that is given some data and some classification, right? Maybe a human has told the computer initially, here are some examples and here are what their category is. Then when you get new ones, it has to use the information that it has in the first initially to decide where the new ones go. So this is a classification problem. If the computer can figure out what the classification is based on training examples, then it is learning. It's using machine learning, and that's a simple example of what machine learning is in order to classify new items as they come in. Classification has broad applications. If you've ever had a credit card company call you and say, "We think that your card might be using fraudulently," well, how did that happen? Well, that's automatic fraud detection based on looking at a lot of metrics on how different people use their credit cards, them recognizing and labeling that certain patterns of usage are correlated with fraud. They found that your credit card was used with similar patterns, and so they said maybe this one is fraud, and so they called you. Voice recognition is classification. If I say the word hello, how does a computer know that it is actually the word H-E-L-L-O? Well, if you have many recordings of people saying hello that are labeled, you can start to say, okay, well this wave signature is correlated with hello. Then when I say hello and you record that, you say which recorded word is it most like? And you try and say, it's a lot like this one. And so we say hello. Who's a terrorist? Right? Well, again, you look at various patterns of what people do and you try and correlate it with what you know. Classification is hugely important. There are lots of other ways that we can apply algorithms to create artificial intelligence. Search is a really important one. Here's a really simple example of search, which is start to type in something in Google and it predicts what it is you might be saying. This is a simple kind of search because this is just basically looking at lots and lots of data, lots of things that other people have typed in, and figure out which is the most likely that you're going to type in based on searching through the data set that you have from what others. But search gets much more complicated. Suppose you want to play chess against a computer, and the computer is deciding what move to make. Well, in a game as simple as chess, you probably know there are many possible moves. How do you decide which move to do? If you were to actually look at every single possible move, and if, depending on what they moved, then what we might do, and if they moved and we made a choice, then what their possible choices were, and you look ahead at possible different moves, you get kind of a tree of possible future movements. You can evaluate the quality of each move. That is, like, the computer wants to pick a move where it looks like it's going to do well. And then based on that, wherever I'm going to go, it wants to make sure that I don't have a lot of good choices. And then based on wherever I go, it has to make a move and it wants to make sure it does have good choices. It can come up with a metric that evaluates the quality of each board and explores this tree. Simply evaluating the entire tree is too big. There's so many possible moves in chess that you could not respond quickly enough. And so part of what AI search is about is to do it efficiently, so you can prune the tree and not investigate every possible outcome. But suppose you did want to investigate what every possible outcome might look like. What does an algorithm even look like to explore that tree?